Here we'll set up a demonstration of a two-dimensional flow in a porous media for Darcy's law to illustrate the use of an alternative approach for calculating boundary fluxes, alternative to the Lagrange multiplier approach. Seems that the Lagrange multiplier approach is very sensitive to the initial conditions, and so you can end up not having a convergence of the solution. So this other approach appears to be less sensitive to those initial conditions. So here we've opened up the COMSOL model. We'll choose a 2D domain just as an example, and we'll look at of course porous media flow and Darcy's law. And we'll do for steady state in this example. We'll look at a geometry with a square. So just again, it's just a two-dimensional domain, rectangular shape, and what we'll have is flow going from the top to the bottom. We'll use hydraulic head as being our dependent variable. First, set up the fluid properties. So the fluid density is 1,000 kilograms per cubic meter. Don't really need to assign the porosity, but I will. And then the permeability is defined by the hydraulic conductivity, which we'll say is 5 times 10 to the minus 4 meters per second. Alright, so all boundaries here, the vertical boundaries of this domain are going to be impermeable. The lateral boundaries will be, or the horizontal boundaries, the top and bottom will both be permeable, and we'll have specified hydraulic head at them. So we'll go in here and specify those hydraulic head conditions. First one is for the top boundary, and here we'll set that as 1 meter, and the bottom one, or the other one, is for the bottom boundary, which we'll set as 0 meters hydraulic head. To use the Lagrange multiplier approach for the to calculate the boundary fluxes, we define, or we would be using weak constraints, but here we'll not do that, just simply because it seems in some cases to cause convergence of solutions at very close to or at the initial condition. Instead, we're going to calculate boundary fluxes by an alternative method, which the user's documentation for COMSOL describes as being just another approach, an alternative approach. And it's not clear to me exactly how it does that calculation, but it does yield the same results that the Lagrange multiplier approach yields. So that's gives me some confidence that it is working properly. Here we want to make sure that we can that the things that we have visualized or showing, that we will be using the discretization tab, so we do want to have that show up, and we will be using that to set the option to have the boundary fluxes calculated accurately. Alright, one of the things that we'll do here is make sure that the gravity is turned off, because I mean, we could have it on, but here, because I specified the hydraulic head at the top boundary to be 1, I don't really need gravity to drive the flow. So here we've got the gravity effect turned off. The place where we'll implement the computing boundary fluxes is this tab right here, which with it, if we click on it, it will ask if we want to smooth the boundary fluxes, and we can do that if we wish. Don't need to do that, but for right now we'll just leave this off just to show a calculation without that, and we'll use linear elements. So for the discretization here, we'll be using linear finite elements. These can be anywhere from quadratic, cubic, quartic, or quintic. Okay, so first order, second order, third order, fourth order, or fifth order. Okay, so we've got our boundary conditions set. For the initial condition, we're going to set the hydraulic head to be equal to 0 at steady state, so it doesn't really matter because we'll get a solution very rapidly anyhow. Okay, so let's go ahead and perform the study, and for that we'll set the initial condition. And for this, we want to be able to plot the surface. Instead of pressure head, we're going to have it plot the hydraulic head. Alright, let's go back here, and at boundary 3, actually I want to make it a little bit more interesting. By instead of just setting a uniform hydraulic head of 1 at the top boundary, we're going to set a condition such that the hydraulic head is 0 at the 2 corners, but it's a maximum of 1 at the very center of the domain. So here that would be defined by this. Okay, we got this, it's like an if statement which says that the hydraulic head will be equal to 2 times the position x if x is less than or equal to 0.5, and it'll be equal to equal to 2 times 1 minus x if x is greater than 0.5. So it'll vary between 1 and 0 on to the right hand side of this the center line of this domain. So it'll be 0 to 1 from the left hand side to the center line, and from 1 to 0 on the right hand side of that. So we'll expect to have, of course, the highest flux in the middle, and actually there will be negative fluxes. Flow will be coming around like this and up around the side, and we'll see that from a streamline plot. Okay, so that's our hydraulic head in the middle. Alright, so let's go ahead and look at this study. We'll get the initial condition, which is the same as what we just showed a moment ago, and then we'll do the calculation. And here's what it looks like. Basically, you can see that we're going to have this flow going like this, and of course there'll be flow going through the bottom boundary. I do this because by having this non-uniform hydraulic head on the top surface, we'll have more irregularity in the flux, and that's more difficult for just the pure Darcy fluxes. To use the pure Darcy fluxes to compute the flux across the boundaries, and this procedure for calculating accurate fluxes will be superior to using the Darcy fluxes to calculate the fluxes across the boundaries. Okay, we could also show on here another plot, which would be the streamlines. Yeah, here another 2D plot. And for this one, we'll do a contour, or streamline rather. Yeah. For this, we need to use the Darcy fluxes. So there's the streamlines. You can see that of course, the hydraulic head is very as a maximum at the center, and so we're going to have fluxes that are coming like this, and of course, fluxes will go in this pattern on either side of that. So there'll be actual flux up out of the top boundary along the edges here, and of course, it's downward otherwise. So that makes for an interesting flow pattern. As I mentioned, if we calculate the fluxes across this boundary and across the bottom boundary using just the conventional Darcy fluxes, we'll find that they're not going to be the same. The net flux across the top boundary will not be equal to the net flux across the bottom. Because of steady state flow, those two fluxes should have the same magnitude. One will be positive, one will be negative. So there will be a there would be a mass balance error associated with that. All right, so let's look at that. Basically, what we'll do is we'll add some derived results, and that's going to just be a line integration. We're going to integrate the flux across the top boundary, and we'll also do that for the bottom boundary. And here the vertical Darcy flux across the top boundary, and we'll just duplicate this, and we'll do it for the bottom boundary as well. Yeah. So here we can evaluate it for the top boundary. Well, I get 0. Now why is that? I do not know. Okay, the problem is that I chose the wrong flux, because this is a two-dimensional problem, so we don't have a z direction flux. We have a x and a y direction flux, and we're looking at the flux in the y direction. So for the top surface, the flux is this is the velocity. So we'd need to multiply that number times 1,000, so to give you 0.262 kilograms per meter. The per meter would be the depth into the screen, because this is a two-dimensional problem, per second. So that's the that's not the velocity. This is the integrated flux across the top boundary, but you need, that is the volumetric flux. You need to multiply it by the density to get you the mass flux, and we will be using the mass flux later. Now if we do that for the bottom boundary, oh, again, I've got to change this. Alright, let's do it over again so we can see them both. We get minus 2.62 times 10 to the minus 4 for the top boundary. For the bottom boundary, I get minus 2.489. So it's obvious that there's an error there, that those two numbers are not the same. Here it is a velocity, so the velocity has a direction. So when you calculate the flux, it's obviously here it's downward. The velocity is downward here, and it's downward here. So it's coming in up here, and it's coming down here. Later, when we talk about the boundary fluxes using this other method, it actually accounts for whether the flux is going in or out of the boundary, and the sign on the number will tell you as to whether it's going in or out of the domain. And I'll make that clear when I talk about it later. I'm going to duplicate this twice again, because we're going to now go back and we're going to calculate those the boundary fluxes so we get accurate values of them. And here we go down again to the Darcy model, and now we're going to compute boundary fluxes. We could do apply smoothing to the boundary fluxes. I really haven't investigated how much benefit there is from that, so you could or maybe not do that. I don't think that it'll affect the integral of the flux. It may affect whether or not there's some choppiness to the distribution of the fluxes. So smoothing might help just in terms of making the distribution less choppy. Maybe we'll plot that out here. So we'll redo the study again so we get some numbers to do this calculation. Alright, so now we're going to look at not the Darcy flux, but what's under here as being the boundary flux. Okay, so that's boundary 2, and here, or maybe we'll do this from boundary 3. Just to keep them in the right order. And then this one is for boundary 2. I think I might go back and redo these two integrations, and instead of using the Darcy flux, we'll actually, well, we'll see what happens. Just to illustrate what happens, I think I need to go back and recalculate them without choosing the accurate boundary fluxes to show the effect of not having that accurate boundary flux. So I'll show that here in a moment. So for boundary 3, here I'll just eliminate or clear that table that we have here, so we'll be able to examine it. And so this is boundary 3. The mass flux is minus 0.24889 kilograms per meter per second. And for the boundary 2, we get 0.24889. So they're exactly the same magnitude. The negative means that the flux is, a negative sign means the net flux is into the domain. A positive sign means the net flux is out of the domain. That's just the sign convention that is used here. Let's see what happens now if I go back. We'll just leave this set up the way it is, and I'm going to go back and calculate those boundary fluxes for kilograms per meter per second, but without that boundary flux, accurate boundary flux selected. We'll just reevaluate it. So here I'm turning that off, and we'll go back and we'll recalculate, and we'll see that those two numbers are no longer going to be the same. Alright, so here I'll close this off. Remember, the magnitude is 0.24889. Shut that one off. And here for the top boundary, it's minus 0.26247 kilograms per meter per second. Alright, so that negative sign means that the flux is into the domain. And here it is for boundary 2, the bottom boundary, and that one's 0.24891, which would be out of the domain. And it's obvious these two numbers are not the same. So when we make the selection here that to compute those accurate boundary fluxes, this was the alternative to using the Lagrange multiplier approach. Maybe just to complete this, we could just go in here and calculate the Lagrange multiplier, which doesn't seem to cause any problem in the case of solving the steady state Laplace equation, because there's initial conditions, but there's no problem with it setting up those initial conditions, as sometimes occurs with the Richards equation. So now we'll get the solution all over again, and now we can come in here and we'll just again duplicate this twice, and well, first time I'll duplicate it, and what we're going to plot here, or we're going to calculate here, is the Lagrange multiplier as was done in a previous video. Okay, so this should be also the accurate flux. This is for boundary 2. I'm going to change that to boundary 3 for right now, just to keep it in that order. And then I'll duplicate that one. And this one we're going to make to be boundary 2. Okay. Alright, so now if we do that integration, I'll recall these numbers right here. We'll do it for number 5. 0.24983 for the top boundary, and minus 0.24983 for the bottom boundary. So those fluxes are exactly the same in magnitude. The difference here is that with the Lagrange multiplier, the positive sign means the flux is going in, and the negative sign means the flux is going out. I'll go back here and we'll reselect. Oh, it's already selected. Never mind. We'll plot these boundary fluxes out. Remember, it's 0.24983. Again, well, if I just evaluate it for these two boundaries here, doesn't fit into the table. Showing it for boundary 3 and for boundary 4, 0.24983. This is with that alternative approach. The numbers are exactly the same magnitude as what we get with the Lagrange multiplier approach. The difference being that the sign on the number is just switched. So for this case, if the sign is negative, it means the flux is in. If it's positive, the flux is out. With the Lagrange multiplier, if the number is positive, then it means the flux is in, and if it's negative, the flux is out. Okay, so it seems to be fairly straightforward to do this calculation and to calculate the accurate fluxes. So I'm going to save this. And I'm going to go and try to do this same thing for the Richards equation application with the RILs. So here again, we need to make sure that the discretization is visible or being shown. And we see that here in the application of the Richards equation. Here gravity effects are on, and under the discretization menu we can compute the boundary fluxes. Now this is a time dependent flow in this case and not steady state. Right. And for this we'll come up with some derived values. Here it's calculating the going to delete that one right there. There's the flux across the bottom boundary. There's the flux across those top boundary values. Here I'm going to calculate the boundary flux. All right. So again, we've selected those boundary fluxes. I'm going to turn off, make sure that the Lagrange multiplier part is turned off, and that's under the specified head condition. And we see here that I've got it turned on right now, and that seems to cause a problem with the solution. I've just turned it off. Right. So I just carried out to 1,000 seconds. can be done for more later. Alright, so I'll save this and get the initial value, and then just we'll run it. Hopefully it goes all the way through. And it does seem to have done that. So this is this is time t is equal to 0 seconds. We want to maybe plot out that surface at let's say 1,000 seconds. So there's what it looks like at 1,000 seconds. Maybe we want to then show this integration over this domain. Okay. And what it does, of course, is it shows the boundary fluxes over the entire domain for the entire time. So that's shown here in this table, and goes out to 1,000 seconds. So that would be the flux. Let's see, I don't know if that's just for one of those boundaries or if it's all of them. Actually, I think it was for just one of those boundaries, so, or maybe it was all of them automatically. But it seemed to work fine. I'm fairly confident that if you were to calculate the change in mass storage of water inside the domain here, and you were to integrate this boundary flux, the change in storage would be equal to that net inflow. Of course, you do have a flux coming out of the bottom here as well, and we'd need to see if that amounts to anything, because it depends on the initial condition as to whether there be any drainage or not. And it looks like there's a mass well, I got to get the correct flux. We got to again look for the boundary flux. Alright, so it's 10 to the minus 6. Whereas when we looked at this one up here, it was something on the order of 10 to the minus 2, 10 to the minus 3. So it's quite a bit larger. There would be some flux coming out of the bottom. So if you took the flux coming in from the top, and you see these are positive, which means that the flux is going out. The other ones were up here were negative, which means that the flux is coming in. If you took the difference between the integrated flux over time from the top boundary, subtract off the integrated flux to the bottom boundary over that time, that difference over that time should be equal to the change in storage of mass within the domain. And that would mean that the solution is globally conservative, which of course is very important to be confident the numerical results are correct. Okay, so that should be enough. Hopefully that'll help.